We've learned to graph the sine and cosine functions as well as the tangent and cotangent functions along with their domain, range, and some other characteristics of the graph. The last two trig functions that we need to look at the graphs of are secant and cosecant. So I think the easiest way to graph either one of these is to remember the reciprocal identities. So let's go ahead and graph the secant function. Remember, always put parentheses around the arguments of your trig function. If you'll recall, the graph of secant is the reciprocal of 1 over the cosine. So secant is 1 over cosine. So what we can do to graph the secant graph is to graph the cosine graph. So let's go ahead and get started with graphing the cosine graph. This is one that we know, hopefully have it memorized, and can just create the graph fairly quickly. So for the cosine graph, we have our quadrantial angles that seem important: pi over 2, pi, 3 pi over 2, 2 pi. We could keep going a little bit if we wanted, 5 pi over 2, and then 3 pi. And in this direction we'd have a negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. So the cosine graph, if you'll recall, has a cosine of 0 is 1, so it starts up here. It kind of looks like the bird wings. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. And if we keep going, it's going to follow that same pattern. It's also going to follow the same pattern in the negative direction. And so I'm just going to put this in with a dotted line. And the reason we're going to use a dotted line is the solid line will be our actual secant graph. So before we can graph the secant graph, we need to make sure we know the cosine graph. And the easiest way to sketch that in is by plotting your quadrantial angles in some ordered pairs. So what we do is, because this is a reciprocal, it builds off of each other. Now notice, because cosine is in the denominator, the cosine of x cannot equal 0 for the secant graph. So everywhere where this is equal to 0, I have a vertical asymptote. So it looks like I have vertical asymptotes at 1 pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, etc. So it looks like odd multiples of pi over 2 are going to be my vertical asymptotes, and we'll formally write that down here in just a little bit. So that's the start of my secant graph, is to graph the cosine graph as its parent graph. Remember that it's 1 over cosine, so wherever the cosine is equal to 0, meaning it's where it crosses the x-axis, I have a vertical asymptote. Now, if we think about it like this point right here, this would mean 1 over the point of 1, which is 1. So this point is on the graph. So every time you have a point of a 1 or a negative 1, the reciprocal of that would be the 1 or the negative 1. So these are all points on the graph. Now let's say this point right here at, we'll call it pi over 4 or something. So we know that the value right here, whatever it is, square root of 2 over 2, and when I flip that, it would flip up top. The reciprocal would come up top, and that point would appear up here then. And these look like horseshoe shapes in between the vertical asymptotes. So whatever point is here, when I flip it, it becomes more than 1. It reciprocates. Now this one I can only put in half of it because I don't have a vertical asymptote on the right hand side. And I don't have a vertical asymptote on the left side. So this is my secant graph. Pretty easy to work with. Now, in terms of a period, it looks like to me the period could go, this shape will reoccur from negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, so it has a period of 2 pi. It's just not a nice little easy 0 to 2 pi to see. So let's go ahead and write down the characteristics of the secant graph. And remember, it's based on the cosine graph. So first of all, the graph is discontinuous or has discontinuities at every odd multiple of pi over 2. So it has vertical asymptotes, at odd multiples of pi over 2. And the way we would write that is x equal 2n plus 1 stands for odd, pi over 2. So that's an interesting characteristic of this graph. It never crosses the x-axis. These dotted lines that you see here are for the cosine graph. The actual graph of the secant never crosses the x-axis. So it has no x-intercepts. Its period is 2 pi. And there's no maximum value and there's no minimum value, so it has no amplitude. It does have some symmetry with respect to the y-axis. If you were to take and fold the graph right along this line, it would be a mirror image on either side of the y-axis. So it has symmetry with respect to the y-axis. And because it has a symmetry with respect to the y-axis, it's called an even function. And so if for an even function, that would be similar to saying the secant of negative x is equal to just the secant of x. Okay? I guess one thing we forgot was the domain and range. That probably would have been most important. I'm going to scoot that up here. I'll move this business down a little bit, and I'll input the domain and range. So for the domain here, it looks like the domain can be anything except for these asymptotes. So it can be all values of x such that x cannot equal odd multiples of pi over 2, where n is an integer. So when we're looking at this and we're trying to set these up, just remember where the asymptotic lines are. Now for our range, it looks like it goes from negative infinity to infinity, and it does, but there's a gap in between there, so we have to watch out for that. So it goes clear down from negative infinity up to a negative 1, but it touches a negative 1, so I have a bracket there, and then it has a big gap, and then it doesn't start up again until 1 where there's a bracket because it actually touches 1 and it heads off toward infinity. So that's the domain and the range of the secant graph. Now when we graph the cosecant function, I'm going to do all things similar, but the reciprocal will be different that I use. So let's go ahead and graph the cosecant graph. Recall that the cosecant graph is 1 over the sine of x, and of course the sine of x cannot equal 0 because it's in the denominator here, so I'll need to watch out for that. So let's go ahead and put up the graph for cosecant. Okay, so we want to start with sine. We want those nice quadrantial angles, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2. I just want to put a lot in here so we can get more than one period. So negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2. And of course these values of 1 and negative 1 are important as well. So for the sine function, the sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi is 0, the sine of 3 pi over 2 is negative 1, and this pattern continues. And again, if you don't know your unit circle, these are going to be really hard for you to graph. So make sure you keep working on that unit circle if you don't have it memorized. Okay, so let's go ahead and put this in with dots. This is our parent graph. It's not our actual graph, so I'm not going to use the solid line. I'm just using this dotted graph to build the cosecant graph off of. Okay. Now, everywhere that crosses the x-axis, that's where the sine is equal to 0, I'm going to have a vertical asymptote. So I have a vertical asymptote at negative 2 pi, at negative pi, and right here along the x-axis, or sorry, the y-axis, so it's kind of hard to see that one, so I'm going to put a little thicker line in there so we can make sure we see that. And then at pi, and at 2 pi, 3 pi. So I see my pattern here. It looks like multiples of pi. And then from here, the reciprocal of 1 would be 1. And this point down here, that let's say a half, when I flip 1/2, 1 divided by a half is 2. It comes up here and I have these horseshoe shapes again. And that's going to move off of each of these maximum and minimums from the sine function. And this is my cosecant graph. And then from here, we can do the same as we did above. We can start talking about its domain, range, etc. So you can see they look very, very similar. The big difference is where their asymptotic lines are. So let's start with the domain here. It looks like the domain can be all values of x such that x cannot equal odd multiples of pi. So the way we would write that is n pi, where n is any integer. Then we can talk about the range. The range goes from negative infinity to infinity with that gap in the middle where the orange parent graph is. So this would go from negative infinity to -1, bracket, union, 1 to infinity. We can also talk about some other things here as our vertical asymptotes. Our vertical asymptotes will occur at any multiple of pi. So I'd have n pi here. And these n values could be positive or negative. So it could be a -2 pi, -3 pi. It could be a positive 2 pi, positive 3 pi. There are no x-intercepts. Also, the period is 2 pi. That's how often it repeats itself. There's no min, there's no max, so there's no amplitude. And then last but not least, the graph is symmetric with respect to the origin, just like the sine graph. And if it's symmetric with respect to the origin, that means it's an odd function. So this looks like cosecant of -x is equal to a negative cosecant of x. So these are the graphs of the secant and the cosecant function, and then we can apply some transformations to these. And when we apply the transformations, they're the same transformations that we looked at before. If you add c, you would shift the graph up c units. If you subtract c, you'd shift the graph down c units. So none of those transformations that we've looked at for sine, cosine, tangent, or cotangent are any different. So instead of listing those again, let's go ahead and just look at the guidelines or the method for sketching the graphs for the cosecant and secant functions. Okay, so these are going to be similar to graphing sine and cosine, and building off of there is basically what we have here. Let's look at our general form. Whoops, everything disappeared on me. Let's look at our general form, and let's do y equal a cosecant bx, and always put parentheses around the arguments of your trig function. My math lab doesn't always do this, but I would want you to do that on quizzes, exams, etc. Y equal a secant of bx. So our strategy here is to graph the reciprocal function as a guide. So that would be your step 1. So this would mean to graph secant of x, graph cosine of x first. To graph cosecant of x, graph sine of x first. Then the next thing you want to do is, after you get those graphed, everywhere those cross the x-axis, you want to put in your vertical asymptotes. So sketch the vertical asymptotes. And basically they'll be wherever they cross the x-axis. Now once we have that filled in, I can go ahead and put in those nice horseshoe shapes that either open up or down. So we sketch the U shapes, and they're not technically a U, they don't go straight up and down. Oh, and then we do this off of the max and mins of the reciprocal. Off of the reciprocal graph. So it's pretty basic. It's just what we just got done working through. So I think the best thing that we can do is to go through a couple of examples and graph them and go through all the steps. So for our first one, let's go ahead and look at, we want to kind of do some little bit harder ones, because you'll definitely run into some harder ones when you're working. So let's do one with 2 transformations. So let's go ahead and graph y equal 2 secant 1/2 x. And remember, this could also be written as y equal 2 secant x over 2. 1/2 x and x over 2 are the same thing. So our first step is going to graph the reciprocal function. So the reciprocal function that we're going to work with is y equal, now the 2 stays, the only thing that reciprocates is the secant, which is 1 over the cosine of 1/2 x. So the 2 stays up top. It doesn't reciprocate. It's not part of the trig function. It's just the number that we drag along. Now in order to graph the reciprocal function, I go through the 4 steps that I usually would go through before. So the 2, the effect of the 2, doesn't apply when we're trying to look at this cosine function. So the way that we really want to think about this is just graphing the parent graph. So this is the reciprocal graph, but what we want to do in order to come up with this reciprocal graph is to graph y equal 2 times the cosine of 1/2 x. And then what we'll do is we'll build off of this. So even though this is the reciprocal graph, if I were to graph or rewrite 2 times the secant of x over 2, it would equal this. But this is the final graph that we get. We want to use this graph right here to build off of. Okay, so be really careful that you just don't think about rewriting this, but you think about reading this as your parent graph. So that's what we'll work on. Okay, so for that parent graph, again we have y equal 2 cosine of 1/2 x. So I have a couple of things going on here. I see 2 transformations. So the first one I see is a vertical stretch. So this 2 And so my new amplitude for this graph is not 1, but it's 2. Now this 1/2 x, what this is going to be, this is going to be horizontal because it's inside the argument of the trig function, and it's going to be a horizontal stretch by a factor of 1 over 1/2, which is 2. So those are the two things that I'm looking for right now. And now we go through and we use the steps from our other four-step method. So our first step for this parent graph again is we would find the period. Now remember, the period is the old period, which is 2 pi divided by this coefficient in front, which is 1/2. So this would be 2 pi divided by 1/2, which is the same as 2 pi times 2 over 1. When you divide by a fraction, you multiply by the reciprocal. So this is 4 pi. Then what I do is I take this period of 4 pi and I want to split it up into quarters. I guess before I split it into quarters, though, I probably better find my start and end points. So what we do is we rewrite our start points for our standard period and our end points, and then I plug in my argument of the function I'm looking at, which is 1/2 x, or x over 2, and I solve for x. So I'm going to multiply the middle and both sides by 2. So I'd get 0 less than or equal to x less than or equal to 4 pi. So this is my start at 0, and this is my end at 4 pi. So as we continue here, we're going to split this into 4 intervals. Now remember, these intervals will give us these 5 key or special numbers, and those will be our max, min, and our midline or our midpoint. So I take 4 pi minus 0 and I split it into quarters. So this tells me pi is the length or width of each quarter. So our start point is equal to 0. Next point is 0 plus pi, which is pi. Our next point after that, I'd start with pi and I'd add pi, 2 pi. Next point after that, I'd start with my old point, which is 2 pi, add pi, and I'd get 3 pi. And our end point would be 3 pi plus pi, which is 4 pi. And so that's working out just like I think it should. So I should go 0 to 4 pi, and that does here. So I'm going to take these points and I'm going to plug them into a table. So I'm going to evaluate the function. At these points. So I'm going to evaluate the function at 0, pi, 2 pi, 3 pi, and 4 pi. So here's x. And I forgot what my function was already. I think it was 2 secant half x. 2 secant 1/2 x. So I'm going to have 1/2 x. Then I'll have secant of 1/2 x, and then I'll have 2 secant of 1/2 x. And again, I'm going to be using these points of 0, pi, 2 pi, 3 pi, and 4 pi. I'm kind of getting too crowded here. 3 pi and 4 pi. Again, my graph was y equal 2 secant 1/2 x. Okay, so if I plug a 0 into 1/2 times 0, I get 0. 1/2 times pi is pi over 2. 1/2 times 2 pi, the 2's cancel and I'm just left with pi. 1/2 times 3 pi is 3 pi over 2. 1/2 times 4 pi is 2 pi. So I'm getting these nice quadrantial angles. Now I'm taking the secant of each one. Now remember, secant is the same as 1 over cosine. So the cosine of 0 is 1. 1 over 1 is going to be 1. So that's my first point. So again, I'm just plugging these values in, and then I'm going to go to my next line to multiply them by 2. Next I do the cosine of pi over 2. The cosine of pi over 2 is 0. 1 over 0 is undefined. You know what? Actually, I forgot what we were doing here. We're not graphing this graph yet. So excuse me, we're doing cosine. I jumped ahead a little bit. So we should be graphing y equal to cosine 1/2 x. So this will be cosine. So I was going to say we shouldn't be getting anything undefined right now. We should be getting undefined in our next steps. Okay, so we're just graphing cosine here because once we get the cosine graph, then we'll graph the secant graph based on that. So sorry about that. Okay, so the zeros, all that stays on the first row. The cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is -1. Cosine of 3 pi over 2 is 0, and the cosine of 2 pi is 1. And then I multiply each of these times 2. Okay? Now the points that I want to graph then are this 0, 2, pi, 0, 2 pi, -2, 3 pi, 0, 4 pi, 2. So again, we want to graph the points 0, 2, pi, 0, 2 pi, -2, 3 pi, 0, 4 pi, 2. Now once we see the pattern here, we might be able to expand that a little bit. So our points of interest look 0, pi, 2 pi, 3 pi, 4 pi on the x-axis. Pi, 2 pi, 3 pi, 4 pi. I'm guessing this will go 5 pi, 6 pi, 7 pi. And I'll go in the other direction as well. -pi, -2 pi, -3 pi, -4 pi, -5 pi. Okay, so I'm going to use y equal to cosine 1/2 x in orange. So 0, 2, that would be this point right here. Pi 0. So it's going to look like this bird shape, the bird wings or the flying bird. 2 pi, -2, 3 pi 0, 4 pi 2. And again, this pattern will continue on both in the positive and in the negative direction. Okay, and I'm just going to fill this in with a dotted line, because remember, this is kind of the structure or the framework And then what I'm going to do then is my next step of the secant graph, anywhere where this graph crosses the x-axis, I have a vertical asymptote. So I put in my vertical asymptotes, and then this graph in red will be the two secant 1/2 x. And then off of the maximum points, I have the horseshoe shape again that's opening up, and off of the minimum points, they're opening down. And this would be the graph of 2 times the secant of 1/2 x. So again, be careful that you're graphing the parent graph. The reciprocal of secant is cosine. I don't rewrite this as 1 over cosine for my parent graph, but do recall that this is equal to 2 times 1 over the cosine of 1/2 x. Okay, this is a rewrite, but the parent graph we want to use is up here. So that's our graph that we're looking at. That's where our vertical asymptotes will go. And these are pretty simple to look at once you get the parent graph graphed correctly. Let's go ahead and do one more example. These do take a while. These are long problems. Let's go ahead and graph y equal 3/2 cosecant, so we'll use cosecant here, x minus pi over 2. Okay, from here we want to figure out what is the parent graph. What do I want to start working with? So let's go ahead and write out our parent graph here, or the reciprocal graph. So what we want to graph is y equal 3/2 cosecant, the reciprocal of cosecant is sine, x minus pi over 2. So this is the graph that we want to look at, and then once we get that graph built, we will sketch the cosecant graph off of that. So to get started, I see two transformations. I see the 3/2, which is a vertical stretch by a factor of 3/2. So our amplitude will change from 1 to 3/2 for the sine graph. And then I also see this x minus pi over 2. This is going to be a phase shift to the right pi over 2 units. So those are the two things that are coming up. But we're going to go ahead and go through this step by step. The new period will be 2 pi over 1, because there's an implied 1 here, or just 2 pi, so the period doesn't change. And then I set up the start and end points for a standard period of the sine curve, and I plug in my argument of my new trig function, x minus pi over 2, and then solve for x. So if I solve for x here, I would add pi over 2 to the middle and to both ends. So the interval I'm looking at is pi over 2 is less than or equal to x is less than or equal to, so if I found a common denominator, this would be 4 pi over 2 plus pi over 2 would be 5 pi over 2. So these are my start and my end points. So for my start, I have pi over 2, and for my end, I have 5 pi over 2. Now next what I want to do is I want to take this interval and split it into quarters. And again, the interval is pi over 2 into quarters. Okay, so that would be 5 pi over 2 minus pi over 2 into quarters divided by 4. So this would be 4 pi over 2 over 4. 4 pi over 2 is the same as 2 pi over 4, which reduces to pi over 2. This is the width of each quarter. Okay, so I have my start point. So my start point was pi over 2, and then I have 3 of these next points. And then I have my end point. Now the end point better be 5 pi over 2 if I'm doing this right. So my next point would be my start point plus the width, which is pi over 2. Pi over 2 plus pi over 2 is 2 pi over 2. 2 pi over 2 reduces to pi. Pi plus pi over 2 is 3 pi over 2. 3 pi over 2 plus pi over 2 is 4 pi over 2, or 2 pi. And 2 pi plus pi over 2 is going to be 5 pi over 2. So this ended right where we thought. So these are our key points or special points that we need to work with. X equal pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. So now what I'll do is I'll put these in a table. So I'll have this table with x's, and I'll have pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Now I need to remember what function we're graphing. I have to be careful. I'm doing the parent function. So this is y equals 3/2 sine x minus pi over 2. So my first thing I'm going to do is I'm just going to evaluate x minus pi over 2. Then I'll evaluate the sine of x minus pi over 2. And then finally I'll take 3/2 times the sine of x minus pi over 2. And this table just kind of breaks this down and makes it a little bit easier to evaluate. So the first thing I'm going to do is I'm going to take each value and then subtract pi over 2 to get these values in my first row. So let's go ahead and plug in. Pi over 2 minus pi over 2 would be 0. Pi minus pi over 2 is pi over 2. 3 pi over 2 minus pi over 2 would be 2 pi over 2, or pi. 2 pi minus pi over 2 is 3 pi over 2. And 5 pi over 2 minus pi over 2 is 4 pi over 2, or 2 pi. So I get these nice quadrantial angles again. Okay, so then I want the sine of each one. The sine of 0 is 0. The sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And the sine of 2 pi is 0. Then I take each of these times 3/2. Okay, now I plot these ordered pairs. And the ordered pairs I want to plot are pi over 2, 0, pi, 3/2, 3 pi over 2, 0, 2 pi, -3/2, and 5 pi over 2, 0. So again, those ordered pairs are pi over 2, 0, pi, 3/2, 3 pi over 2, 0, 2 pi, -3/2, and 5 pi over 2, 0. Now remember, I have to, when I graph this, I have to make sure I have enough room to do the reciprocal, so I have room to flip this up. Okay, so it looks like my important points are multiples of pi over 2. So I have pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and of course if I wanted to keep going, 3 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2. And I'm just going to mark this as 3/2 right here, just to make it easy. So at pi over 2, I'm at 0. At pi, I'm at 3/2. At 3 pi over 2, I'm back to 0. At 2 pi, I'm at -3/2. 5 pi over 2, 0. And this pattern will continue. Now remember, this isn't my actual graph, this is the parent graph. So this will go in with a dotted line. Then everywhere it crosses the x-axis will be a vertical asymptote for my cosecant graph. So this is the sine curve. It's just the sine curve moved over from what I'm used to seeing, pi over 2 units. Okay, so now let's go ahead and sketch in those vertical asymptotes. Everywhere it crosses the x-axis, I have a vertical asymptote. And then off of the maximum points, this opens up. And off of the minimum points, it opens down. And there's the graph of my cosecant function. So this is the graph of y equals 3/2 cosecant of x minus pi over 2. So again, pay close attention to how you build the parent or the reciprocal graph, and then the secant or cosecant graph will build pretty easily off of that. So be careful, pay attention to those details, make sure you know your unit circle. If you don't know your unit circle, make sure you're working on it constantly, because it will make all of this graphing and all of this a lot easier. As usual, please let me know if you have questions, and good luck.